Thanks everyone to the organizers. I'll be talking about 1As from the near infrared perspective. So what we can learn from mainly from the near infrared light curves. So this is a project I've been working on for in the last year or so. So just as an introduction, when we observe Type Ia Supernovae, we see that in the infrared they show this very prominent secondary peak, right? So here on the right, I'm comparing. You can see like the optical light curves on the infrared, and as we go to the infrared, they start developing this secondary peak, and which is mainly driven by a change in ionization of iron group elements like iron and cobalt. So this is similar to the recombination in Type II supernovae, which they develop this plateau phase. So this is similar, and this change in ionization mainly produces photons at near infrared wavelength. Now, if we go into the physics, like a bit more into the physics behind this, we see that different physical properties can modify this second peak, right? So things like metallicity, mixing, and nickel mass can change how prominent and also like how early or late this second peak is. So on the right, you see the effect of nickel mass, for example, from Kaysen 2006. So as you can see, the infrared is ideal for studying Type Ia supernovae and learning about their physics. Now, when we go to observational properties, we see that those supernovae that are brighter, both in the optical and the infrared, they also show a more prominent secondary peak, and also at later epochs. And as we go to fainter Type Ia supernovae, for example, in even going to 91 BGs, we see that this second peak starts appearing at earlier epochs, and even like merging in the most extreme cases. Right. And well, also we know that Type Ia are sort of like pseudo standard candles in the infrared. So this is ideal for cosmology, of course. And they are like quite homogeneous, in part due to the effect of dust extinction, which is lessened at this wavelength. So this is not only great for cosmology, but also like great for studying, for example, the environment or like separating dust, like extrinsic and intrinsic properties of 1As. Right. So with this like brief introduction, hopefully you can see that the infrared observations are a very powerful tool for studying 1As, right? They study their physics, their progenitors. So yeah, there's like a lot of information we can get from these observations, especially from the second peak. And I have been focusing on this project in particular. So fortunately, in the last decade or so, the number of Type Ia supernovae observed at the infrared wavelength has greatly increased. So there are different surveys. Most of them are public. So here on the right, I am showing some like subsamples of different surveys. I'm only showing those like only counting 1As that have at least 5 near infrared epochs. The only survey that is not public is CSP2 in this case. So CSP1 is public, but CSP2 is private still. But yeah, the only like downside is that the number of Type Ia supernovae that have well-covered infrared light curves is not large. So again, on the right, these are only 1As which have at least 5 near infrared epochs. Now, this doesn't mean that the first and second peak are covered. Some of them only have the first peak, or some of them only have the second peak covered, for example. But still, we have some, let's say, decent number of well-covered Type 1As. And in particular, CSP is a great survey for this. So here I'm showing all the 1As from this survey. On the left, we have the light curves, and on the right, we have the color curves. So we know that 1As are quite homogeneous in the infrared, but this is only true around first peak. As we go to the second peak, we see that there's quite a large diversity, like a large spread, these secondary peak. So of course, there's a lot we can learn from these, and also from the color curves. And this project in particular, I'm going to be using some principal component analysis. So before I talked about these analyses, first we want to have like somewhat complete light curves. So usually, according to Smalley, you fit 1As with like light curve feeders like SALT3, SALT2, or Snoopy. However, for this project, I don't want to have any, I don't want to assume any underlying models for the light curves. So I'm using Piscola, which is a data-driven light curve feeder based on Gaussian process. And on the right, you can see some, of course, some of the nice examples here. So these are supernovae which have first and second peak more or less well covered. And these fits with the Piscola. So again, I'm not assuming any template here. It is all data-driven. Now, before I apply some PCA, principal component analysis on the light curves, I do some pre-processing. So I am doing these analyses independently for each near-infrared band. So I'm showing here only for the Y and the J band. So I shift all the near-infrared bands such that they agree on the time of first peak, and also normalize them so they all have the same magnitude of peak. Right, so I'm focusing here on the diversity of the second peak, and then I apply PCA to these subsamples here. So these are again well-covered Type Ias. On the right, we can see like the three components. First three components of these the PCA, and we can see that with the first two components, we already captured pretty much all the diversity. So I would consider in this case the third component as just like some noise within the data. But we focus, for example, on the first component. We see that those supernovae which brighter secondary peak also have these peak at later epochs, and those with fainter peaks have the peak at earlier epochs. And we see the same sort of pattern here in the Y and in the J band. Now, this second component, this middle component here, can be a bit harder to interpret, but for as I don't have much time, I'll just be focusing on this first component. Right, so we can actually plot these this component versus different light properties, light parameters. So in this case, I'm plotting this first component. So this is for the Y band versus the peak absolute magnitude. This SPV, which is the color stretch obtained using Snoopy. So this is a combination of the stretch, is X1, for example, and color of the supernovae. On the right, this is pseudo color, so peak brightness in the Y band minus peak brightness in the J band. And at least from these correlations in here, we see that there's a relatively strong correlation between this first component and this SPV, this color stretch parameter. Now, if we go back to this first component, so this component is telling us about like how prominent and how early or late this second peak is happening, and this correlates with this color stretch. Now, this is not quite new. If we go back to 2015, Supernova 1 found this correlation between I believe it was the peak brightness of the second peak and the stretch delta 15 of Type Ia Supernovae. And we can also trace this correlation to the amount of nickel mass, for instance, of Type Ia Supernovae. So we know that those 1As that are brighter also have more nickel mass. And again, it means that the secondary peak will occur at later epochs. So we believe that this correlation is just tracing this correlation with nickel mass. Now, of course, there are like a lot of other parameters that we can test in here, like nickel mass or like host galaxy mass, color, environmental properties. So again, this is all a work in preparation. Again, for the sake of time, I'll skip back to this very last slide. So of course, we can also do a direct comparison of models. Also, if you have a model that produces output light curves, you can compare those directly to the observations And in this case, I'm showing this double detonation model with the helium shell from Christine Collins here at Trinity. Now I'm putting these together with a few Type Ia supernovae. So I think it would be very nice to have like more models that produce outputs in the infrared. So from what I understand, there's a lack of models working in the infrared. Of course, most of them are focused on the optical, but it would be nice to have some more models focused on the infrared to put some like nice constraints on the projector scenarios, on the explosion physics of these events. And I will just leave the conclusions here. Thank you very much.